This video is going to shift gears from area of a region to volume of a solid of revolution using the disk method. The learning target we are going to focus on is finding the volume of a solid of revolution using the disk method. There are a few videos that you can access through Khan Academy as well. Each one of them has a link. This is a 9-minute video on the disk method around the x-axis. It's a nice video for visual purposes. So if you're having a hard time visualizing how something two-dimensional becomes three-dimensional, this video will be helpful. The second video also will help visualize and generalize the process. And the third video will show the disk method around something other than the x-axis, a horizontal line. I'm going to work through my notes. So our objective is to find the volume of an irregular solid formed by revolving a region in the coordinate plane around a line of revolution. We'll go straight to an example. Suppose the region bounded by the function r of x equals the square root of x, and it's called r of x for a reason. That's not random. We're doing that specifically because r is going to reference something, and you'll see that shortly. X equals 1, x equals 4 on the x-axis. We're going to take that region and we are going to revolve it around the x-axis. So if I jump back to one of the Khan Academy videos, you can kind of see that it would be like taking a region that we could graph and then rotating it around the x-axis so that it becomes a solid that, instead of having an area, has a volume. This one would kind of look like a cone. And you'll see that if you watch the video. So how do we do this? Well, let me walk you through the process. This would be the region that was mentioned up here. So a sketch has the square root of x from x equals 1 to x equals 4 and the x-axis. And our goal is to take that region and revolve it around the x-axis so that it creates almost like a cup type shape that is solid. So you could physically pick it up if it was something that we could create. And the way that we're going to come about the formula for doing this is we're going to start by saying, let's just look at one portion of the graph. Let's just look at this region right here that I'm scanning over. And you can see that I've labeled it as r of x. So it is some height from the x-axis to the square root of x. And if I wanted to just take that and revolve just that around the x-axis, what it would create is a really thin cylinder. To help you visualize that, it would be like taking this and rotating it around and around and around so that it created this really thin cylinder. Thin is relative right now as my pen is making this thicker than I would like to, but we could then find the volume of that really thin cylinder. How? Geometry. The formula for the volume of a cylinder is pi r squared, which would give us the area of the circular region, times our height. In this case, because it's a really thin cylinder, our height is very small. We need to generalize this so that we can use it in the coordinate plane. So our radius is actually the value of the function, r of x. So we replace the radius from the geometric formula with r of x. So I mentioned earlier that I used r for our function in this case for a reason, so that you would recognize that the function actually represents the radius of any given disk, any given cylinder in this region. And we call them disks. You can think of it almost like a frisbee golf. I think you guys call that frolfing. Think of a frisbee golf disc where it is circular with a very thin height to it, if you will, and that's the shape that you can envision. You could also think of, if you slice a donut, not a donut with a hole in the middle, we'll get to something like that later, but if it was a donut that didn't have a hole in it and you just took one slice through the middle of the donut, not cut it in half, but through the middle, it would be a really thin cylinder. So our radius ends up being the function. And our height, that really, really small, thin part of our height, is our change in x. So we have to have some substance to this cylinder. Otherwise, it wouldn't have a volume. And you can see that I wrote in here, that's our change in x. So if we just wanted to find the volume of this real thin cylinder, just this small portion of our graph that we have here, then we would take pi times the value of our function, which represents our radius, squared, times the change in x, which represents our height. Now, I'm going to erase that. Because I want to find the volume of the entire solid all through there. If I want the entire solid all the way through there, then I'm going to have to do it for all of the really thin cylinders in this region. So we set up a summation. If we want the volume of not just one disk, but the entire solid, we are going to sum all of the volumes of our cylinders. So if I started with one cylinder and went to n cylinders, that would allow me to get an approximation. So let's say I did it with 2 cylinders. Okay, if I made 2 relatively big cylinders using maybe this radius here and the radius over here when x is 4, I would get an approximation, but it wouldn't be exact because my cylinders would come over the top. So it would be an over approximation. So I take pi, because that's just a coefficient, put it out front of my summation, and let's say I want all of the cylinders. Then I can take the limit as n approaches infinity, so that I have every single cylinder in the region. Well, what happens when we take the limit as n approaches infinity of a summation? The summation turns into an integral. So we have a formula for finding the volume of a solid revolved around the x-axis, and that formula is pi times the integral from a to b of our function squared, because our function represents our radius, with respect to x, which represents our height. And for me at least, this formula is very easy to remember, because all I think about is the formula for the volume of a cylinder. Pi r squared times height. This only works if we're revolving around something that is horizontal. So we can only use this if we're revolving around the x-axis or another horizontal line. We can then finish this problem pretty easily, because all we need to do is the integral from 1 to 4, and don't forget the pi out front, of our function, which was the square root of x squared dx, which is highlighted right here. And then the work for this, the pi stays out front. We simplify, the square root of x squared just becomes x, and now it's an integral. So the integral of x is x squared times 1/2, or x squared over 2. We evaluate that from, well, we do the upper limit first minus the lower limit. Could have also taken the 1/2 out if you wanted and put pi over 2 in front, and then you wouldn't have to deal with the fractions in there. Or you can just leave it as x squared over 2. Either way you do it, 16 halves minus 1/2 is 15 halves, times the pi gives you 15 pi over 2. This can also be done easily in the graphing calculator. So we could do the integral from 1 to 4 of x with respect to x. And I'll just do that quickly on the main screen. I'm not even going to put the functions in. I'm just going to say pi math option 9. So pi times the integral of my function was x after I squared the square root with respect to x from 1 to 4. 23.562 would be the approximation, and as you can see in the notes, there it is. A relatively simple process as long as you know the formula and understand where it comes from. We can use this for all kinds of problems. So the next example in the notes is find the volume of the region bounded by f of x equals the square root of sine of x equals 0, x equals pi in the x-axis that is revolved around the x-axis. So here's our graph. That's the square root of the sine of x from 0 to pi, coming back to the x-axis, and we are revolving this around the x-axis. Since we're revolving around the x-axis, we use the formula from above. So it's pi times the integral from 0 to pi of our function squared dx. Pretty simple one, because the square root of sine of x squared is the sine of x, and now it's just a nice little integral problem. So the pi stays out front. The integral of sine is negative cosine. We evaluate the upper limit minus the lower limit, and as long as you know your unit circle values and you're careful with your negative signs, you end up getting 1 plus 1, which is 2 times the pi, so 2 pi. Again, this could also be done very easily in your graphing calculator. You wouldn't see 2 pi show up. It would give you the approximation, 6.28 something, I believe. And even though you don't need units, keep in mind that we're now doing volume. So if you had to do units, it would be units cubed. There's another example here that I could walk you through. In the interest of time, I'm going to do it very quickly, but if you were asked to find the volume of the region bounded by the function 6 minus x squared in the x-axis, you weren't given x values. So similar to some of the area problems we did earlier, you would set 6 minus x squared equal to 0, which is the value of the x-axis, so that you could find where those functions intersect. They happen to intersect at plus or minus the square root of 6, which is where I came up with the graph. So we've got the parabola opening down, intersecting the x-axis at negative square root of 6, and positive square root of 6. So if we were revolving this around the x-axis, the integral would be pi times the integral from negative square root of 6 to positive square root of 6 of our function squared. In this case, we would have to simplify. 6 minus x squared, we'd have to multiply it out. There'd be a lot of work with this one. And then it would be, a big function. Now, you might notice I changed the pi to a 2 pi. And the reason I did that has to do with symmetry. If you take a look at this region up here, the right and the left-hand sides have the same amount of area. So instead of doing the integral from negative square root of 6 to positive square root of 6, I split it in half and doubled my volume. So when I changed this pi to a 2 pi, I also changed my lower limit to 0, my upper limit to the square root of 6, so that when I went through the work, I only had to deal with one square root of 6 instead of a negative as well.